Right now, you are falling. Not through space, not toward Earth, but through time itself. Every second that passes, a star somewhere in the universe collapses. Its core, crushed by gravity beyond all comprehension, enters a state that breaks reality. 10 kilometers wide, the mass of our sun, spinning faster than a Formula One engine. Magnetic fields strong enough to atomize your body from 1,000 kilometers away. They are called neutron stars. And they are not simply stellar remnants. They are the universe's most violent survivors, the corpses of giants that refuse to die. Cosmic zombies that pulse, scream, and detonate with energies that make nuclear weapons look like birthday candles. Some spin 600 times per second. Others erupt with magnetic cataclysms that can be felt across the galaxy. A few steal matter from companion stars, feeding on their partners like cosmic vampires. And then there are the silent ones, the invisible predators drifting through the void, emitting nothing, detectable only when they warp space-time itself. Science recognizes at least 7 distinct types, each more extreme than the last, each a window into physics at its absolute breaking point. From pulsars to magnetars, from cannibals to ghosts, these objects define the edge of what matter can endure before it surrenders entirely and becomes a black hole. This is not theory, this is measurement. And what we have measured is terrifying. In 1967, a graduate student named Jocelyn Bell was scanning radio data from a telescope in Cambridge when she noticed something that made no sense. A signal, repeating every 1.337 seconds. Perfectly regular, unnaturally precise. For weeks, her supervisor, Anthony Hewish, entertained the possibility that it might be aliens. They called it LGM-1. Little green men. But the truth was far stranger than extraterrestrial communication. What Bell had discovered was the first pulsar, a neutron star so precise in its rotation that it functions as the most accurate clock in the universe. Pulsars are rotation-powered neutron stars. When a massive star, at least 8 times heavier than our sun, exhausts its nuclear fuel, its core collapses in less than a second. The outer layers detonate in a supernova, briefly outshining entire galaxies. What remains is a sphere roughly 20 kilometers across, containing more mass than our sun. The density is so extreme that a single teaspoon would weigh approximately 1 billion tons on Earth. Imagine compressing Mount Everest into the size of a sugar cube. Now multiply that compression by a factor of 10 million. But density is not what makes pulsars remarkable, it is their rotation. When the star collapses, the conservation of angular momentum causes it to spin faster, just as an ice skater spins faster when they pull their arms inward. A star that once rotated every 30 days now completes a full rotation in seconds. Some pulsars spin over 600 times per second. At their equators, the surface velocity approaches 15% the speed of light. The magnetic field collapses with the star, concentrating into an almost incomprehensible intensity. A typical pulsar has a magnetic field 1 trillion times stronger than Earth's. This field does not align with the rotation axis. As the star spins, the misaligned magnetic poles sweep through space like a lighthouse beam, channeling charged particles along magnetic field lines. These particles, accelerated to near-light speed, emit electromagnetic radiation across the entire spectrum: radio waves, visible light, X-rays, gamma rays. When that beam sweeps across Earth, we detect it as a pulse, 1 flash per rotation. Hence the name, pulsating star, shortened to pulsar. The Crab pulsar, located in the center of the Crab Nebula, is perhaps the most studied neutron star in existence. It was born in the year 1054, when Chinese astronomers recorded a guest star so bright it was visible during the day for 23 days. Today, that pulsar rotates 30 times per second, powering the entire nebula with its rotational energy. Astronomers have observed it pulsing in radio, optical, X-ray, and gamma-ray wavelengths. It is losing rotational energy at a rate of 5 billion trillion watts. That is 30,000 times the total power output of our Sun, all radiating from an object the size of a city. Over 3,000 pulsars have been cataloged in our galaxy. Most have periods between 0.1 and 2 seconds. They are extraordinarily stable. The best pulsars rival atomic clocks in precision, deviating by less than 1 microsecond per year. This stability has profound applications. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar system, PSRB 1913+16, where two neutron stars orbit each other every 7.75 hours. By timing the pulses with extreme precision, they measured the orbital decay caused by gravitational wave emission, providing the first indirect proof of Einstein's prediction. They won the Nobel Prize in 1993, but rotation-powered pulsars are not eternal. As they radiate energy, they slow down. Their magnetic fields gradually weaken. After 10 million years, most pulsars cross what astronomers call the death line, a threshold where they can no longer generate enough electromagnetic radiation to be detectable. They do not disappear, they simply go dark, becoming invisible neutron stars drifting silently through the galaxy, their lighthouses extinguished. Except some of them do not stay dead. In 1982, astronomers discovered something that violated everything they thought they knew about pulsar evolution. A neutron star designated PSRB 1937+21 was spinning 641 times per second, not per minute, per second. This was impossible. Pulsars are supposed to slow down over time. Yet here was an object rotating faster than any pulsar ever observed, completing one full revolution every 1.5 milliseconds. At its equator, the surface was moving at nearly 1/4 the speed of light. Any faster and centrifugal force would tear the star apart. The discovery forced astrophysicists to reconsider everything. These objects became known as millisecond pulsars, and their existence revealed a process so bizarre it borders on cosmic vampirism. Millisecond pulsars are not young. They are ancient neutron stars that have been brought back from the dead. The mechanism is called recycling, and it requires a victim. Most millisecond pulsars exist in binary systems with a companion star. Billions of years ago, the neutron star was an ordinary pulsar, spinning down gradually as it radiated energy. It crossed the death line. Its lighthouse went dark. It became a cosmic ghost. But then its companion star evolved. As the companion expanded into a red giant, its outer layers began to spill over the gravitational boundary known as the Roche lobe. Material flowed from the companion onto the neutron star, forming an accretion disk, a swirling vortex of superheated gas spiraling inward at millions of degrees. As this material fell onto the neutron star, it transferred angular momentum. The dead pulsar began to spin up, faster and faster. Over millions of years, the neutron star consumed enough matter to accelerate its rotation from once every few seconds to hundreds of times per second. During this feeding phase, the system is visible as a low-mass X-ray binary. The infalling material, heated by friction and gravitational compression, emits powerful X-rays. Astronomers have detected these systems and observed them in the act of recycling. Some, called accreting millisecond X-ray pulsars, show coherent pulsations in X-rays, proving that the neutron star's magnetic field is already channeling material onto its poles. Eventually, the companion is consumed. What remains is a rapidly spinning neutron star with a weak magnetic field and a dead or dying stellar remnant in orbit. A millisecond pulsar can continue spinning for tens of billions of years, far longer than the current age of the universe. The fastest known pulsar, PSRJ 174824446 AD, discovered in the globular cluster Tarzan 5 in 2004, rotates 716 times per second. At this rate, a point on its equator is moving at approximately 24% the speed of light. This is close to the theoretical maximum. If a neutron star spun any faster, gravitational waves or centrifugal forces would destabilize it. Some physicists believe that neutron stars cannot exceed 730 rotations per second without flying apart or emitting gravitational radiation that would slow them down. Globular clusters are breeding grounds for millisecond pulsars. These ancient, densely packed star clusters contain hundreds of thousands of stars crammed into a sphere only tens of light years across. The stellar density is so high that close encounters and collisions are common. A neutron star can capture a companion or steal one from another binary system through gravitational interactions. The globular cluster Tarzan 5 alone contains 37 millisecond pulsars. The cluster 47 Tucanae hosts 22. But not all millisecond pulsars are content to simply spin. Some continue feeding, even after reactivating as radio pulsars. These systems, called Black Widow or redback pulsars, are actively destroying their companions. The intense radiation and particle wind from the pulsar heats the companion star to extreme temperatures, evaporating its outer layers. Some companions have been reduced to less than 2% the mass of our Sun, slowly being consumed entirely. Astronomers have observed eclipses in these systems, as the evaporated material temporarily blocks the pulsar's radio signal. Millisecond pulsars are not gentle. They are proof that in the universe, even death is temporary if you are willing to feed on the living. On March 5, 1979, something hit Earth from space. It was not an asteroid. It was not a solar flare. It was a burst of gamma radiation so intense that it overwhelmed every detector on the planet. The Soviet spacecraft Venera 11 and Venera 12, in orbit around Venus, registered radiation levels that spiked from 100 counts per second to over 200,000 in a fraction of a millisecond. Satellites across the solar system recorded the blast. Even the Pioneer Venus orbiter, shielded behind an entire planet, detected it. The source was 50,000 light-years away. A neutron star, designated SGRO 526-66, had just unleashed more energy in 1/10 of a second than our Sun will emit in 1,000 years. This was humanity's introduction to magnetars. They are neutron stars, but calling them neutron stars is like calling a nuclear bomb a firecracker. They possess the strongest magnetic fields in the known universe. A typical neutron star has a surface magnetic field of around 100 million Tesla. A magnetar's field exceeds 100 billion Tesla. That is 1,000 times stronger than an ordinary neutron star and a quadrillion times stronger than Earth's magnetic field. At such intensities, physics stops behaving. Quantum electrodynamics, the theory governing light and matter, predicts that above a critical threshold of 4.4 × 10⁻13 Gauss, photons can spontaneously split into particle-antiparticle pairs. Space itself becomes birefringent, meaning light traveling through the magnetar's field is polarized and split into separate beams. Atoms are compressed into needle-like shapes, forced into cylindrical configurations by the magnetic pressure. The vacuum itself warps. If you were 1,000 kilometers from a magnetar, its magnetic field would be strong enough to disassemble you at the molecular level. The atomic bonds holding your body together would be ripped apart by magnetic forces. Your constituent atoms would be stretched into elongated rods. Your electrons would be stripped away. You would not die. You would simply cease to exist as a coherent structure. Magnetars are born during the most violent core collapse supernovae. When a star at least 25 times the mass of our Sun explodes, the collapsing core generates a proto-neutron star rotating hundreds of times per second. If conditions are precisely right, a dynamo mechanism can develop. The rapid rotation, combined with convective motions and extreme temperatures exceeding 1 trillion degrees, amplifies the magnetic field through a process not fully understood. Within seconds of birth, the field reaches magnetar strength. Only about 10% of neutron stars are born as magnetars. Approximately 30 have been confirmed in our galaxy, though the true number is likely higher. Many may have gone dormant before we developed the instruments to detect them. The magnetic field is not stable. It is under immense tension, twisted into complex topologies by the star's rotation and internal dynamics. The neutron star's crust, composed of crystallized iron nuclei, is locked to the magnetic field. Any change in the field stresses the crust. Eventually, something has to give. When the crust fractures, the event is called a starquake. The crack propagates through the neutron star's surface at the speed of sound in nuclear matter, roughly 1/3 the speed of light. The magnetic field lines snap and reconnect violently, releasing stored magnetic energy in a catastrophic eruption. These events are detected as soft gamma repeaters, bursts of low-energy gamma rays and hard X-rays lasting a fraction of a second. But sometimes, the eruption is far worse. On December 27, 2004, the magnetar SGR 1806-20 experienced the largest starquake ever recorded. For 1/10 of a second, it released more energy than the Sun has emitted in the last 100,000 years. The gamma-ray flux was so intense it ionized Earth's upper atmosphere, temporarily disrupting radio communications. The flare originated from a neutron star 47,000 light-years away. Had it occurred within 10 light-years of Earth, the radiation would have triggered a mass extinction event, stripping away the ozone layer and sterilizing the surface. The flare was powered entirely by magnetic energy. The magnetic field had released approximately 10 to the 46th joules in a fraction of a second. For comparison, the total energy output of our Sun over its entire 10 billion-year lifetime is around 10 to the 44 joules. The magnetar released 100 times that amount in 1/10 of a second. Magnetars do not last. The magnetic field decays over time, dissipating through ohmic resistance and particle winds. After roughly 10,000 years, the field weakens to the point where starquakes cease. The magnetar transitions into a quieter phase, resembling an ordinary neutron star. But for those 10,000 years, it is the most dangerous object in the galaxy. In 2020, astronomers detected a fast radio burst, an enigmatic pulse of radio energy lasting milliseconds, originating from the magnetar SGR 1935 plus 2154 in our own galaxy. This was the first confirmed link between magnetars and fast radio bursts, mysterious signals previously detected only from distant galaxies. The implications are staggering. If magnetars produce fast radio bursts, then these signals, once thought to be exotic cosmological phenomena, might simply be the death screams of magnetic fields collapsing under their own impossibility. Magnetars are not stellar remnants. They are stellar disasters, frozen in a state of perpetual catastrophe. There is a star system called Centaurus X3, located roughly 30,000 light-years away, where something monstrous is happening. Every 4.84 seconds, a pulse of X-rays sweeps across space. The source is a neutron star, but it is not alone. It orbits a massive blue supergiant star, circling it every 2.09 days, and as it orbits, it feeds. The neutron star is stealing matter from its companion. Gas from the supergiant's outer atmosphere flows across the gravitational boundary between the two stars, spiraling down toward the neutron star in a disk of plasma heated to tens of millions of degrees. As this material crashes onto the neutron star's surface at nearly half the speed of light, it releases gravitational potential energy equivalent to detonating several thousand nuclear weapons every second. The emission is almost entirely in X-rays. This is an X-ray binary pulsar, also called an accretion-powered pulsar. Unlike rotation-powered pulsars, which generate energy by slowing down, these neutron stars are powered by consumption. They are cosmic vampires, locked in orbital embraces with companion stars, draining them over millions of years. The neutron star in Centaurus X3 was discovered in 1971 by the Uhuru satellite, the first X-ray observatory ever launched. It was only the second pulsar ever found outside the radio spectrum, and the first accretion-powered pulsar ever identified. Its discovery proved that neutron stars could exist in binary systems and that they could power themselves through accretion rather than rotation. The mechanism is elegant and violent. The neutron star's magnetic field, typically around 100 million Tesla, is strong enough to disrupt the accretion disk at a distance of several thousand kilometers from the surface. Material cannot flow freely onto the star. Instead, the magnetic field channels it along field lines toward the magnetic poles, creating two accretion columns where plasma slams into the surface. These impact zones heat to billions of degrees, emitting intense X-rays. As the neutron star rotates, the hot spots sweep through space like searchlights, creating the observed pulsations. The pulse period reveals the neutron star's spin. In Centaurus X3, that period is 4.84 seconds. This is far slower than rotation-powered pulsars, which spin in milliseconds or seconds. But X-ray pulsars are not slowing down. Many are spinning up, accelerated by the angular momentum transferred from the accreting material. Some show erratic spin behavior alternating between spin-up and spin-down over months or years, depending on the accretion rate. The companion stars in these systems come in two varieties. High-mass X-ray binaries contain massive stars, typically O or B-type giants, with more than 10 times the mass of our Sun. These stars lose mass through powerful stellar winds, or through Roche lobe overflow when they evolve into supergiants. The neutron star captures this material and feeds. Her X1, another famous X-ray pulsar discovered in 1971, fits this category. Its companion is a star with approximately 2.2 solar masses, and the neutron star has a mass of roughly 1.5 suns. It rotates every 1.24 seconds, and the entire system is eclipsed every 1.7 days as the companion star blocks our view. Low-mass X-ray binaries contain less massive companions, typically stars similar to or smaller than our Sun. These systems evolve more slowly. The companion gradually transfers mass to the neutron star over billions of years. Many millisecond pulsars are thought to be the end products of low-mass X-ray binaries, neutron stars that have finished feeding and reactivated as radio pulsars. Some X-ray pulsars are transient. They orbit massive B stars, blue giants that rotate so rapidly they shed disks of gas around their equators. The neutron star's orbit is highly elliptical. When it passes through the B star's disk, it captures material and briefly becomes an X-ray source. Then it swings away, the accretion stops, and the system goes dark. These outbursts can last weeks or months before the neutron star returns to quiescence. The accretion process is not always stable. If the accretion rate drops below a critical threshold, the magnetic field expands outward and begins to act like a propeller, flinging material away instead of allowing it to accrete. The neutron star enters a propeller phase, where it neither accretes efficiently nor emits strong X-rays. If the accretion rate increases too much, the radiation pressure from the infalling material can halt further accretion entirely, creating an upper limit called the Eddington limit. In February 2008, astronomers announced the discovery of a neutron star that behaves as both a magnetar and a pulsar. Observations from NASA's Rossi X-ray Timing Explorer and other instruments detected a neutron star emitting both rotation-powered radio pulses and magnetically powered bursts typical of magnetars. This discovery shattered the clean boundaries between neutron star types. It suggested that magnetars are not a distinct class, but may represent a phase in the life of some pulsars, potentially reversible depending on the star's magnetic field evolution and accretion history. X-ray binary pulsars will not feed forever. If the companion is massive, it will eventually exhaust its nuclear fuel and explode as a supernova. If the binary survives, the result is a double neutron star system. If the companion is low mass, the neutron star will consume it entirely, either evaporating it through radiation or merging with it, leaving behind a solitary millisecond pulsar. These systems are laboratories for extreme physics. They allow astronomers to measure neutron star masses with extraordinary precision by analyzing orbital dynamics. Several neutron stars in binary systems have confirmed masses exceeding 2 solar masses, placing critical constraints on the equation of state of nuclear matter. They reveal what happens inside a neutron star's core, where densities surpass those of atomic nuclei and matter exists in states that cannot be replicated in any terrestrial laboratory. X-ray binary pulsars are not just feeding, they are testing the limits of matter itself. There is a neutron star called Geminga, approximately 800 light-years from Earth, that should not be detectable. It emits no radio waves. For decades, it was invisible to radio telescopes, the instruments that had discovered every other pulsar. And yet, Geminga is one of the brightest gamma-ray sources in the sky. Its name is not random. In the Milanese dialect, Geminga means, "it's not there." Astronomers chose the name because they could not find it. In 1972, the small astronomy satellite detected a powerful gamma-ray source with no visible counterpart. No star, no nebula, nothing. Just gamma rays emanating from apparently empty space. It was designated Geminga, the ghost. It took until 1992 for astronomers to confirm what it was. Using data from the Röntgen satellite, they detected X-ray pulsations with a period of 0.237 seconds. Geminga was a neutron star, rotating roughly 4 times per second, emitting pulses of high-energy radiation. But at radio frequencies, it was completely silent. This was the first confirmed radio-quiet neutron star, and its discovery revealed a terrifying possibility. Most neutron stars in the galaxy might be invisible. Radio-quiet neutron stars are neutron stars that do not emit detectable radio waves, or emit them in directions that never sweep past Earth. The prevailing theory for pulsars assumes that the radio beam is narrow, confined to a cone around the magnetic poles. If the magnetic axis is aligned in such a way that the beam never crosses our line of sight, we will never detect radio emission, even though the neutron star is actively radiating. This is called the lighthouse effect in reverse. If the lighthouse beam never points toward you, you will never see the light. But geometry cannot explain every radio-quiet neutron star. Some objects emit thermal X-rays, indicating they are young and hot, but produce no radio emission at all. These neutron stars are not simply misaligned, they are genuinely silent in the radio spectrum. Astronomers have identified a small group of neutron stars called X-ray dim isolated neutron stars, or XDINSs, informally known as the Magnificent Seven. These 7 objects were discovered by the ROSAT and XMM Newton X-ray observatories. They are nearby, within a few thousand light-years, and they emit soft thermal X-rays consistent with surface temperatures of around 1 million degrees. They are isolated, not in binary systems, and they show no signs of supernova remnants. They are simply drifting through space, cooling slowly, emitting faint X-rays and nothing else. Their rotation periods range from 3 to 12 seconds, far slower than typical pulsars but faster than magnetars. Their magnetic fields are estimated at around 100 billion to 1 trillion Tesla, intermediate between ordinary neutron stars and magnetars. They do not emit radio pulses. They do not flare like magnetars. They simply exist, faintly glowing in X-rays, invisible to almost every other form of observation. One member of the Magnificent Seven, RxJO 720.4-3125, exhibits a peculiar behavior. Its X-ray spectrum changes over time, cycling through different temperature profiles on a timescale of years. This suggests that the neutron star's surface is not uniform, possibly marked by hotspots or magnetic anomalies that drift in and out of view as the star precesses. The cause remains unknown. The existence of radio-quiet neutron stars has profound implications. If a significant fraction of neutron stars are radio-quiet, then our census of the neutron star population is catastrophically incomplete. Radio surveys have detected approximately 3,000 pulsars in the Milky Way, but theoretical models predict there should be roughly 100 million neutron stars in the galaxy, based on supernova rates and stellar evolution models. That means we have detected roughly 0.003% of the total population. The remaining 99.997% are invisible. They could be radio-quiet. They could be oriented such that their beams miss Earth. They could be old, their rotation period so long that they no longer generate detectable radiation. Or they could be dormant, their magnetic fields decayed, their surfaces cooled to the point where thermal emission has shifted into the infrared, beyond the sensitivity of current X-ray telescopes. In May 2025, astronomers using the Meerkat radio telescope detected a coherent radio burst from a neutron star in the Carina Nebula, designated 2XMMJ 104608.7-594306. This neutron star had been observed for years in X-rays but was assumed to be radio-quiet. The burst lasted only milliseconds, sharp and intense, completely unlike the steady pulsations of typical radio pulsars. It resembled the transient bursts seen from magnetars, suggesting that some radio-quiet neutron stars may emit sporadic, unpredictable radio signals that previous surveys missed. This discovery implies that radio-quiet neutron stars are not truly silent. They may emit occasionally, in bursts too brief or too infrequent to be caught by traditional pulsar surveys, which rely on detecting periodic signals. If this is common, then the galaxy is filled with neutron stars emitting rare, random radio flashes, invisible except to telescopes monitoring the sky continuously. Another subset of radio-quiet neutron stars are the central compact objects, or CCOs, found at the centers of supernova remnants. Unlike typical pulsars, CCOs do not show pulsations in radio or optical light. They emit only soft X-rays, indicating hot surfaces but no evidence of active rotation-powered emission. They are young, born within the last few thousand years, yet they are already radio-silent. Some models suggest that CCOs are neutron stars with unusually weak magnetic fields below the threshold required for pulsar emission. Others propose that they are neutron stars observed pole-on, such that their radiation beams point directly at us, smearing out any pulsations into steady emission. The most disturbing possibility is that some neutron stars are genuinely dormant. After millions of years, a neutron star's magnetic field decays. Its rotation slows. Its surface cools to a few 100,000 degrees, and its thermal emission shifts into the mid-infrared, a wavelength range where telescopes struggle to detect faint point sources against the background glow of interstellar dust. These neutron stars would be functionally invisible, detectable only through gravitational microlensing if they happen to pass in front of a background star, or through their gravitational influence on nearby objects. Radio-quiet neutron stars are not absent. They are everywhere, drifting unseen through the galaxy, emitting signals we cannot detect or are not equipped to recognize. They are the majority, the hidden population, the silent dead that outnumber the lighthouses 1,000 to 1. In 1995, astronomers identified a problem. A group of neutron stars were emitting powerful X-rays and pulsating with periods of several seconds, behaviors consistent with X-ray binary pulsars. But there was no companion star, no accretion disk, no source of infalling matter. These neutron stars were isolated, yet they were radiating X-ray luminosities far exceeding what their spin-down rates could provide. They were designated anomalous X-ray pulsars, or AXPs, because nothing about them made sense. An ordinary rotation-powered pulsar loses energy as it slows down. The rate of energy loss can be calculated from the pulsar's period and the rate at which that period increases. For most pulsars, the energy radiated away matches the energy lost from rotation. The books balance. But AXPs radiate 100 to 1,000 times more energy than their rotation can supply. The energy has to come from somewhere else. The leading explanation is that AXPs are magnetars in disguise. They possess ultra-strong magnetic fields on the order of 100 billion to 1 trillion Tesla. But they have not yet experienced the catastrophic starquakes typical of soft gamma repeaters. Instead, they radiate energy continuously through the slow decay and reconfiguration of their magnetic fields. The twisting and untwisting of field lines heats the neutron star's crust, generating X-rays that escape into space. This places AXPs in an uncomfortable middle ground between rotation-powered pulsars and magnetars. They are too luminous to be standard pulsars, yet too stable to be classified as soft gamma repeaters. Some researchers argue that AXPs represent an evolutionary phase, a magnetar in its youth before the field becomes unstable enough to produce major flares. Others suggest they are magnetars viewed from a particular angle, where the geometry of the magnetic field prevents us from seeing the most violent eruptions. Approximately a dozen AXPs have been confirmed. They rotate slowly with periods between 6 and 12 seconds, far slower than millisecond pulsars, but faster than most magnetars. Their X-ray emission is steady, pulsating with their rotation period but not exhibiting the dramatic bursts characteristic of magnetars. However, several AXPs have been observed to flare unexpectedly, emitting short bursts of hard X-rays and gamma rays. Behavior that blurs the line between AXPs and soft gamma repeaters even further. One of the best studied AXPs is 1E2259 plus 586, located in the supernova remnant CTB109, approximately 10,000 light-years away. It rotates every 6 more seconds, a spin period that is increasing at a measurable rate. In 2002, it experienced a glitch, a sudden increase in rotation rate caused by a starquake in the neutron star's crust. The glitch was accompanied by a burst of X-rays and a temporary brightening that lasted several weeks. Then, unexpectedly, the pulsar experienced an anti-glitch, a sudden decrease in rotation rate, something that had never been observed before in any neutron star. The event suggested that the interior of the neutron star is differentiated, with a solid crust and a superfluid core that can rotate independently, occasionally exchanging angular momentum in unpredictable ways. The magnetic field in an AXP is not static. It evolves over time, undergoing instabilities driven by the decay of electric currents in the neutron star's crust and core. As the field reconfigures, it can twist into increasingly complex topologies, storing energy that is eventually released as heat or electromagnetic radiation. The timescale for this process is thousands to tens of thousands of years, meaning AXPs may eventually transition into soft gamma repeaters as their fields become more unstable, or fade into ordinary neutron stars as the fields decay below critical thresholds. Another anomalous object, 4U0142+61, exhibits behavior that defies easy classification. It emits X-rays with a luminosity roughly 1,000 times greater than its spin-down power. It has a rotation period of 8.7 seconds and a magnetic field estimated at 1 trillion Tesla, firmly in magnetar territory. But it has never been observed to produce a magnetar-like flare. Instead, it emits steadily, pulsating like clockwork, year after year. Infrared observations have detected excess emission from the system, suggesting the presence of a dusty disk or debris field orbiting the neutron star. Possibly the remnants of a companion star, or fallback material from the supernova that created it. The existence of AXPs raises a fundamental question about neutron star taxonomy. Are these objects a distinct class? Or are they simply magnetars observed during a particular phase of evolution? Recent evidence suggests the latter. In 2008, astronomers discovered that the neutron star Swift J 1834.9-0846 exhibited behavior consistent with both a pulsar and a magnetar. It emitted rotation-powered radio pulses, but also displayed magnetar-like X-ray bursts. This hybrid nature suggests that the boundaries between pulsar types are not rigid. A neutron star can transition between states depending on its magnetic field configuration, accretion history, and internal dynamics. Some models propose that all neutron stars are born with strong magnetic fields, but the field strength decays over time at different rates depending on the star's initial conditions. In this scenario, magnetars are simply young neutron stars with the strongest fields. AXPs are middle-aged neutron stars with moderately strong fields, and ordinary pulsars are older neutron stars with weaker fields. The observed diversity would then reflect differences in age and initial magnetic field strength rather than fundamentally different formation mechanisms. But this model has problems. If AXPs are simply aging magnetars, we should observe a smooth continuum of properties between magnetars, AXPs, and ordinary pulsars. Instead, we see gaps. The magnetic field strengths cluster into distinct groups. The rotation periods fall into separate ranges. The X-ray luminosities do not follow a simple evolutionary track. Something about the physics of magnetic field decay or internal structure is creating discrete classes rather than a continuous spectrum. Anomalous X-ray pulsars are not anomalies. They are evidence that the neutron star zoo is more complex than any simple classification can capture. They are hybrids, transitional objects, witnesses to processes we do not yet understand. In 1974, two radio astronomers, Russell Hulse and Joseph Taylor, discovered something extraordinary while surveying the sky with the Arecibo telescope. They detected a pulsar, PSRB 1913+16, spinning 59 times per second, but its pulses were not regular. The period varied rhythmically. Doppler shifted by orbital motion. The pulsar was in a binary system, orbiting an unseen companion every 7.75 hours. The companion was invisible to telescopes. It emitted no light, no X-rays, no radio signals, but from the orbital dynamics, its mass could be calculated: 1.4 solar masses. The only object that massive and that invisible is a neutron star. This was the first confirmed double neutron star binary, two stellar corpses locked in a gravitational death spiral. The system is doomed. General relativity predicts that orbiting masses emit gravitational waves, ripples in spacetime that carry energy away from the system. As energy is lost, the orbit shrinks. The two neutron stars spiral closer together. Hulse and Taylor measured the orbital decay with exquisite precision over decades. The orbital period was decreasing by 76 microseconds per year, exactly matching Einstein's predictions. This provided the first indirect evidence for gravitational waves. In 1993, they won the Nobel Prize in Physics. PSRB 1913+16 will continue spiraling inward for another 300 million years. Then, the two neutron stars will collide. The merger of two neutron stars is one of the most violent events in the universe, exceeded only by supernova explosions and gamma-ray bursts. As the stars approach, tidal forces begin to distort them. Their solid crusts crack and deform. When they are roughly 100 kilometers apart, they are orbiting each other hundreds of times per second, their surfaces moving at significant fractions of the speed of light. The gravitational wave emission becomes catastrophic, draining the orbit in seconds. At the moment of contact, the collision releases energy equivalent to the total output of every star in the observable universe combined. The merged object, now a hypermassive neutron star or a rapidly forming black hole, ejects a small fraction of its mass into space. This ejected material, heated to billions of degrees and compressed to nuclear densities, undergoes rapid neutron capture nucleosynthesis. Heavy elements, gold, platinum, uranium, are forged in seconds. The ejected material glows for days, emitting a kilonova, the thermal afterglow visible across billions of light years. On August 17, 2017, humanity witnessed this process for the first time. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from two neutron stars merging in a galaxy 130 million light-years away. The signal lasted 100 seconds, during which the inspiral could be tracked in exquisite detail. 2 seconds after the gravitational wave signal ended, the Fermi Gamma Ray Space Telescope detected a short gamma-ray burst from the same location. Within hours, telescopes across the world observed an optical transient, the kilonova, glowing in the galaxy NGC 4993. This single event confirmed decades of theory. Neutron star mergers produce gravitational waves, they produce gamma-ray bursts, they synthesize heavy elements. The gold in your jewelry, the platinum in catalytic converters, the uranium in nuclear reactors, all of it was forged in neutron star collisions billions of years ago. 15 double neutron star systems are currently known in our galaxy. Most were discovered through radio pulsar timing. The orbital periods range from 90 minutes to several hundred days. The shortest period system, PSR J07373039, is the most remarkable. Discovered in 2003, it consists of two pulsars, both detectable as radio sources. They orbit each other every 2.4 hours with an orbital separation of only 800,000 kilometers, roughly twice the distance from Earth to the Moon. At this separation, the gravitational field is so intense that the spacetime curvature causes the orbit to precess, rotating its orientation by 16 degrees per year. The system is a laboratory for testing general relativity in the strong field regime. But PSR J07373039 is also a preview of destruction. The orbit is shrinking by 7 millimeters per day. In 85 million years, the two neutron stars will merge. The energy released will briefly outshine every star in the galaxy. Not all double neutron star binaries survive. The formation process is inherently unstable. The first neutron star forms when a massive star in a binary system explodes as a supernova. If the explosion is asymmetric, the neutron star receives a natal kick, a velocity imparted by the anisotropic ejection of matter during the collapse. Kicks can exceed 1,000 kilometers per second. If the kick is too strong, the binary is disrupted and the two stars fly apart, becoming isolated neutron stars. If the binary survives the first supernova, the neutron star begins accreting material from its companion, spinning up into a millisecond pulsar. Millions of years later, the companion exhausts its nuclear fuel and explodes as a second supernova. Again, the neutron star receives a kick. Again, the binary may be disrupted. Simulations suggest that only 10 to 20% of systems survive both supernovae to become double neutron star binaries. The survivors are rare treasures for astrophysics. They allow precise measurements of neutron star masses. The masses cluster around 1.33 solar masses, with some exceeding 2 solar masses. These measurements constrain the neutron star equation of state, the relationship between pressure and density in the core. They reveal whether neutron star interiors contain exotic matter, strange quarks, or phase transitions to deconfined quark-gluon plasma. Double neutron star systems are also gravitational wave sirens. LIGO and its successor observatories will detect hundreds of mergers per year once they reach full sensitivity. Each detection provides a measurement of the neutron star masses, spins, and tidal deformability. The tidal deformability, how much a neutron star distorts under tidal forces during the inspiral, directly probes the star's internal structure. Stiff equations of state, where matter resists compression, produce larger tidal deformations. Soft equations of state produce smaller deformations. The August 2017 detection constrained the tidal deformability with enough precision to rule out several proposed equations of state. It suggested that neutron star radii are roughly 11 to 13 kilometers, narrowing the range of possible internal compositions. Future detections will refine this further, potentially revealing whether neutron stars contain quark matter cores or remain purely hadronic throughout. Double neutron star systems are not eternal. They are countdowns. Every orbit brings them closer. Every rotation radiates energy into spacetime. They are not stable structures. They are collisions in progress, separated from destruction only by time. In 2006, astronomers at Jocelyn Bell's original observatory made a discovery that should not have been possible. They detected radio pulses from neutron stars that were not pulsing regularly. The signals appeared sporadically, sometimes emitting one strong burst, then vanishing for hours or days before appearing again. The periods were normal, a few seconds per rotation, but the emission was wildly erratic. They called these objects rotating radio transients, or RRATs. RRATs violate the fundamental assumption of pulsar astronomy that neutron stars emit steady, clock-like pulses. For decades, pulsar surveys were designed to detect periodic signals, sources that pulse with metronomic regularity, but RRATs pulse only occasionally, perhaps once every few hundred rotations, or even less frequently. If your telescope happens to be observing during one of the long gaps between pulses, you will detect nothing. The neutron star is invisible. The first RRATs were discovered by reanalyzing archival data from pulsar surveys. Astronomers developed algorithms to search for single bright pulses rather than periodic signals. When they applied these algorithms to years of stored observations, RRATs appeared in the data by the dozens. They had been there all along, emitting their sporadic signals, but the surveys had been blind to them. Approximately 200 RRATs have been identified. Their rotation periods range from a few tenths of a second to several seconds, similar to ordinary pulsars. But their emission is unpredictable. Some RRATs emit a detectable pulse every few minutes. Others go silent for hours. The longest observed gap between pulses from a single RRAT exceeded 3 hours, meaning the neutron star completed over 5,000 rotations without emitting a single detectable radio pulse. The mechanism behind this erratic emission is unknown. One hypothesis is that RRATs represent a transitional state between active pulsars and dead neutron stars. As a pulsar ages and its magnetic field weakens, the conditions for generating radio emission become marginal. The emission switches on and off depending on subtle changes in the magnetosphere, possibly triggered by starquakes or variations in the particle density above the polar caps. In this model, RRATs are old pulsars flickering at the edge of the death line, occasionally mustering enough energy to produce a pulse before falling silent again. Another possibility is that RRATs are simply ordinary pulsars observed from an unfavorable geometry. If the radio beam is extremely narrow and the alignment is such that only the edge of the beam sweeps past Earth, we might detect pulses only when random fluctuations in the beam intensity happen to exceed our detection threshold. Most of the time, the beam is too weak to register. Occasionally, a brighter pulse gets through. But this explanation has problems. Some RRATs show highly variable pulse amplitudes. One pulse might be 100 times brighter than the next. The pulse arrival times are irregular, suggesting that the neutron star's rotation is not perfectly stable, or that the emission regions are moving around on the star's surface. Neither behavior is consistent with the stable, narrowly beamed emission expected from ordinary pulsars. What makes RRATs truly unsettling is their population. If neutron stars spend a significant fraction of their lives in an RRAT phase, then the number of RRATs in the galaxy could be enormous, far exceeding the number of detectable pulsars. Surveys designed to find periodic signals would miss them entirely. They would be invisible, detectable only through rare, random pulses that most telescopes would never catch. In 2022, astronomers discovered an object that pushed the boundaries even further. Using the Australian Square Kilometre Array Pathfinder, they detected radio pulses from a source designated ASKAPJ 183-90756. The pulse is repeated every 6.45 hours, not seconds, hours. This is a neutron star rotating once every 6.45 hours, emitting radio pulses that can be detected across interstellar space. This should be impossible. According to pulsar theory, a neutron star rotating this slowly should be far below the deathline, incapable of generating the electromagnetic fields necessary for radio emission. Its magnetic field should have decayed. Its magnetosphere should be dead, it should be silent. But it is not silent. It emits bright, coherent radio pulses, stronger than many millisecond pulsars. The emission is not constant. The pulses appear for several weeks, then vanish for months, suggesting that the neutron star is transitioning between active and inactive states. The mechanism is unknown. Some researchers propose that ASK-APJ-18390756 is a magnetar, its ultra-strong magnetic field, allowing it to generate emission even at such slow rotation rates. Others suggest it might be a white dwarf, not a neutron star at all, though the emission characteristics do not match known white dwarf behavior. Long-period pulsars like ASK-APJ-18390756 reveal a terrifying gap in our understanding. We thought we knew when neutron stars stopped emitting. We thought the death line was a hard boundary, a threshold below which radio emission was impossible. But ASK-APJ-18390756 proves otherwise. Neutron stars can remain active far longer than theory predicts. They can emit sporadically, unpredictably, in ways that our models do not account for. If long-period pulsars are common, then the galaxy is filled with neutron stars that pulse once per hour, once per day, once per week. They would be invisible to traditional pulsar surveys, which observe sources for only a few minutes at a time. Only wide-field radio telescopes operating continuously, monitoring large swaths of sky for months or years, would have a chance of detecting them. Projects like the Square Kilometer Array, when fully operational, will revolutionize our ability to find these objects. But until then, they remain ghosts. Neutron stars that pulse once in the time it takes you to watch a movie, emitting signals we are not yet equipped to recognize. RRATs and long-period pulsars are not exceptions. They are evidence that neutron star emission is far stranger and more diverse than the clean categories we have imposed on it. They are the objects at the edge of detectability, the ones that defy our instruments and our theories. They are reminders that the majority of neutron stars are not like the Crab pulsar, bright and steady and impossible to miss. They are faint, erratic, and nearly invisible, and they outnumber the bright ones by orders of magnitude. The universe has been manufacturing neutron stars for 13 billion years. Every supernova that does not produce a black hole leaves one behind. Based on supernova rates and stellar evolution models, astronomers estimate that the Milky Way contains between 100 million and 1 billion neutron stars. We have detected approximately 3,000. This is not a margin of error. This is a census failure of catastrophic proportions. 99.9% of neutron stars are invisible to us. They are out there, drifting through the galaxy, emitting signals we cannot detect or are not designed to recognize. Some are dead, their rotation slowed to the point where emission has ceased. Some are misaligned, their beams pointed away from Earth. Some pulse erratically, once per hour or once per day, in patterns our surveys cannot capture. And some may be emitting in wavelengths we are not monitoring, or using physics we do not yet understand. The neutron stars we have found represent the brightest, youngest, most active fraction of the population. The Crab pulsar, millisecond pulsars, Magnetars, These are the cosmic lighthouses, impossible to miss. But they are outliers. The typical neutron star is not like them. The typical neutron star is old, cold, dim, and silent. It has been coasting through space for millions or billions of years, its magnetic field decayed, its rotation slowed, its surface cooled to a few 100,000 Kelvin. Its thermal emission is in the infrared, undetectable against the background glow of interstellar dust. It produces no radio pulses, no X-rays, no gamma rays. It is functionally invisible. The only way to detect such an object is through gravitational effects. If it passes in front of a background star, its gravity will bend the starlight, causing a brief brightening known as gravitational microlensing. The effect lasts hours to days, depending on the neutron star's velocity and distance. Projects like the optical gravitational lensing experiment have detected thousands of microlensing events, most caused by ordinary stars or brown dwarfs. But a fraction, perhaps 1%, could be caused by neutron stars or black holes. We cannot tell the difference without additional observations. Another detection method is astrometry, measuring the positions of stars with extreme precision. If a neutron star passes near a background star, its gravity will deflect the star's apparent position by a tiny amount, measured in micro-arcseconds. The Gaia Space Telescope, launched in 2013, has measured the positions of over 1 billion stars with unprecedented precision. Analysis of this data may eventually reveal the gravitational signatures of nearby neutron stars, allowing us to map their distribution even when they emit no light. But these methods are slow and inefficient. Microlensing events are rare. Astrometric deflections are subtle. To build a complete census of neutron stars, we need better instruments. We need telescopes that can detect faint thermal emission in the mid-infrared. We need radio surveys that monitor the entire sky continuously for weeks or months, searching for sporadic pulses and long-period transients. We need gravitational wave detectors sensitive enough to capture the mergers of neutron stars across the entire observable universe. Some of these instruments are being built. The square-kilometer array, when completed, will be the most sensitive radio telescope ever constructed, capable of detecting pulsars and transients at unprecedented distances. The James Webb Space Telescope is already observing in the infrared, though it is not optimized for finding faint point sources. Next-generation gravitational wave detectors like Einstein Telescope and Cosmic Explorer will detect neutron star mergers at cosmological distances, providing a complete census of mergers throughout the history of the universe. But even with these instruments, we will not find them all. Some neutron stars are too old, too cold, too far away. Some may have been ejected from the galaxy entirely, flung out by the supernova explosions that created them. Traveling through intergalactic space at thousands of kilometers per second, some may be lurking in regions we cannot observe, hidden behind dense molecular clouds or obscured by the galactic center. And then there are the theoretical uncertainties. We do not know the maximum mass of a neutron star. Observations suggest it is somewhere between 2 and 2.5 solar masses, but the exact value depends on the equation of state, which remains uncertain. Above this mass, a neutron star collapses into a black hole. But the transition might not be instantaneous. Some models predict the existence of supermassive neutron stars, objects temporarily supported by rapid rotation that will collapse once magnetic braking slows them down. If such objects exist, they would be invisible as neutron stars and would eventually become black holes without ever producing a detectable signal. There may also be exotic neutron stars we have not yet imagined. Quark stars, composed of deconfined quark matter rather than neutrons, are predicted by some theories of quantum chromodynamics. They would be denser than neutron stars, with radii of 8 to 10 kilometers instead of 12. Their emission properties might differ from ordinary neutron stars, making them difficult to identify. Hybrid stars, with hadronic outer layers and quark matter cores, are another possibility. These objects would have intermediate properties, potentially explaining some of the anomalous neutron stars that do not fit cleanly into existing categories. The neutron star zoo is not complete. Every new survey reveals new types. RRATs were discovered only in 2006. Long-period pulsars, like ASKAPJ183900756, were found in 2022. Fast radio bursts were first detected in 2007 and only recently linked to magnetars. Each discovery forces us to expand our classification schemes, adding new branches to the evolutionary tree. What we call types of neutron stars may not be discrete categories at all. They may be snapshots of a continuous evolutionary process where a single neutron star transitions through multiple phases over its lifetime. A neutron star might be born as a magnetar, transition into an anomalous X-ray pulsar as its field decays, become an ordinary rotation-powered pulsar, then an RRAT as its emission becomes erratic, and finally falls silent, becoming a radio-quiet thermal emitter before cooling into invisibility. Or the process might not be linear. A dormant neutron star might reactivate if it captures a companion and begins accreting, spinning up into a millisecond pulsar. A millisecond pulsar might evaporate its companion and become a solitary pulsar again. A pulsar might experience a starquake that temporarily increases its magnetic field, causing it to emit magnetar-like bursts before settling back into ordinary pulsar behavior. The point is that we do not know. We have observed only a tiny fraction of the population and only for a few decades. Neutron stars live for trillions of years. We have barely glimpsed the first few moments of their existence. The 7 types described in this script, rotation-powered pulsars, millisecond pulsars, magnetars, X-ray binary pulsars, radio-quiet neutron stars, anomalous X-ray pulsars, and double neutron star systems, are not the full story. They are the neutron stars we have been able to detect and classify with current technology. They are the visible tip of an invisible population. Somewhere in the galaxy, right now, there is a neutron star passing through the space between your location and the nearest star. Its gravity is warping space-time. Its surface is emitting faint infrared photons. Its magnetic field, once a quadrillion times stronger than Earth's, has decayed to a whisper. It spins once every few minutes, a relic of a star that exploded before the sun was born. You will never see it. No telescope will ever detect it. It is one of 100 million ghosts, drifting silently through the cosmic dark, invisible and unknowable. And it is not alone.